Okay, so we're going to define a sigma algebra, which is basically going to encode our notion of a well-behaved subset of the power set. Now, we're going to do this on an arbitrary set X. For us right now, X is going to be the real numbers, but later on we'll want to generalize this to other sets. We had up until now been trying to take the entire power set of the real numbers and assign a measure on every element of that power set. We're now sort of compromising on that based on everything that we've seen and agreeing not to attempt to measure every set of real numbers, but instead to measure only a certain subset of that. But we want to make sure that these things, you know, if something is measurable, then it unioned with another measurable set, they should both be measurable, right? If something is measurable, then its complement should be measurable. These are kind of intuitions about, you know, things that would make a good measurable space. So to formally define that, we say that this subset of the power set is a sigma algebra if it contains the empty set, so that kind of in a sense we think the empty set should be measurable. And, you know, later on we'll talk about, you know, it's probably going to have measure 0, but we'll get to that later. We think that if anything is in it, then its complement should be in it, right? Closure under complements. And if you have any countable collection of elements, then their union is in the set. So that's closure under unions, and that defines a sigma algebra. So here are some small examples of sigma algebras. So in fact, we even technically have a sigma algebra on the empty set. So namely, it's this one, right? The set containing the empty set, right? Because that satisfies all of our properties. It contains the empty set. It is closed under complements because the complement, you know, in this universal set, the complement of the empty set just is the empty set again. So it is closed under complements, and it's closed under unions, because if you take unions of the empty set, you just get the empty set, which is already in there. Okay? Slightly less trivial example, a set containing a single element. So we have to give it the empty set, and because it's closed under complements, then we take the complement of the empty set relative to the universal set, which is this now, and we get that. And that's all you really can do. Notice that in this case and in this case, we're just producing the power set of X, right? It's the only possible sigma algebra on the given sets. Now if we take this one, we have a few more options, right? So we could make the sigma algebra as minimal as possible, and you can always do that by taking just the empty set and the universal set. That is always a sigma algebra. You can check that it always satisfies those properties. But we could alternately take the power set, right? And that also will always be a sigma algebra, right? The power set always contains the empty set. And basically, because it contains every possible subset, then sort of trivially it's closed under any possible operation, including complements and unions. Now, this is the first one where it's just big enough to give something interesting, which is a set with 3 elements. So again, we could take the minimal sigma algebra. We could take the power set, that's sort of the maximal sigma algebra. And in between, we have a few choices, right? And here I've demonstrated one particular one. So you always have to have the empty set. Because it's closed under complements, you always have to have the universal set. From here I can make choices, so I go ahead and choose to give it the set containing just 1. Because it has to be closed under complements, I am forced, therefore, to give it also its complement, which is 2, 3. And now I can choose to stop, right? Because as soon as I include anything more, right? If I chose to include the set containing 2, right, the singleton, I'd have to give it the set containing its complement, which would be 1, 3. I would have to give it the union between 1 and 2, which, right, and basically you could generate, right, like with all of that, if I gave it also the set containing just the number 2, I would then be forced to generate all the rest of the power set. And so like that, you know, right, so this, right, so you have the minimal sigma algebra, the maximal one, and there's basically sort of just this one intermediate sized sigma algebra. Of course, we could permute all of the elements, right? So if I had all along just chosen the set containing 2, then I could, you know, just, you know, make sure that it's closed under complements by giving it the set containing 1 and 3 and stop right there, and that would be a sigma algebra. So I mean, we could permute the elements, but if you want an intermediate sized sigma algebra, it's going to be like this one, basically. Okay, so let's move on to a couple bigger examples of sigma algebras. So we'll take an infinite example, namely the natural numbers, and of course we can always, right, no matter what x is, always take the power set to be the sigma algebra. It's worth asking if this is of any use or interest at all, and in fact it is. We won't see, you know, we won't work with it for a long while, but at some point we are going to generalize the concept of measure so that we won't just be trying to measure sets of real numbers, but we'll be trying to measure lots of other kinds of sets. When we do, then one kind of measure that we could take as an example and actually get some nice results out of is measuring basically the counting measure, or, you know, in some sense kind of like a cardinality measure, where, especially if you're dealing with a finite set, it makes a lot of sense. We say that the measure of the set is equal to the number of elements in it, and if it's an infinite set, then of course we would take the measure of the set to be just infinity. Okay, how about an even bigger infinite example, the real numbers? Now, again, we can always take the power set, but we've already, right, the whole point of getting into all of this is that we don't like that choice, and we'd like to have a different choice of sigma algebra in especially this example, but we may not know how to get it. And in fact, it'll be really hard to say exactly what that sigma algebra is without defining some other concepts first. So, for that reason, as build up to trying to get closer and closer to saying which sigma algebra we're actually going to pick to help us deal with the problems that we've been encountering, is we'll define this notion of the sigma algebra generated by a set B, right? So if you take some collection of subsets of the power set, it may or it may not be a sigma algebra because we don't know whether an arbitrary choice satisfies those 3 conditions that we listed. But what we can do is we can form the smallest sigma algebra containing this collection. And what that means is that we're looking for the sigma algebra which contains all of B, right? But it may have to be a little bit bigger in order to make sure that it stays closed under complements and closed under unions and so on. As of right now, this is just a definition, and we don't necessarily know that, that such a sigma algebra exists, right? If you pick any arbitrary x and any arbitrary b contained within the power set of x, how do we know that the smallest sigma algebra containing b exists at all? So that will be a theorem that we'll prove in a few minutes, but that's the definition. Keep in mind, when we say smallest, what we mean is that, actually, to make it easier to talk about, let's write sigma b as the symbol for the sigma algebra generated by b. And so what we're claiming, or what we're going to show, is that this existed as a sigma algebra, and when we say that it's the smallest, what we mean is that if you took any other sigma algebra that contains B, this one will be contained in it, right? So if you took any sigma algebra containing B, this sigma algebra will be a subset of that one. That's what smallest will mean for us. Okay, just as a little bit of warm-up, before proving this theorem about the existence of the sigma algebra generated by B, let's see it a little bit in action, right? In action in one of the simplest, slightly interesting cases, which is, let's go back to this example of a universe with 3 elements, and we took this example of a sigma algebra, and in fact, we could characterize this sigma algebra as the sigma algebra generated by the set containing just the number 1, right? So you need, right, so if you're going to have this thing, you need a sigma algebra. So you couldn't just, so you couldn't just have the set containing the number 1, because that wouldn't be a sigma algebra. You've got to have the empty set. That forces you to have the universal set, right? So when we're building this thing up and looking for the smallest sigma algebra containing the set 1, we know whatever it is, it's going to have to contain these 2 things. It's also going to have to contain the set containing 1. And again, to be a sigma algebra, it has to be closed under complement, so it's going to have to contain that. And we can stop right there, right? There are other sigma algebras that contain the set of 1, namely the power set, but we want the smallest one, and this is it, right? If you go around looking for any other sigma algebra that contains the set of 1, you'll find that this one is contained in that.